In the previous video, we have discussed about quantifiers with restricted domains. And we have discussed that for variables that are universally quantified, then in order for us to meet our restriction, we use conditionals or implications. In other words, the restrictions are made as hypotheses. Okay. Meanwhile, for existentially quantified variables, we make restriction by using an and operator. Okay, so here are some other examples. Suppose we have this universal quantification statement that for all x that are less than 0, x squared is greater than 0. So what does this statement mean in the domain of real numbers? So we assume that any value that may be replaced with x is a real number. Okay. Let us express this statement in English. So for every real number x, wherein x is less than 0, or meaning x is negative, then x squared, or if we take the square of that number, it will be greater than 0. So what it means that if we square a negative number, negative real number, it will result to a positive number. Okay, so we have this statement wherein we will identify the condition or the restriction. So we have the x is less than 0. The number should be less than 0, and its property should be x squared is greater than 0. And we can express that using an equivalent statement using implications. So as you can see here, we have for all x is less than 0 implies that its square is positive. Okay, as you can see, we have made the condition as the hypothesis, or the restriction as the hypothesis. Now, let's have another example. Suppose we have this statement for all y that is not 0, then y cubed is not equal to 0. So what does it mean in the domain of real numbers? So let us try to express this statement in English. So we have for every real number y, with y is not equal to 0, then its y cubed is not equal to 0. So in other words, the cube of every non-zero number is non-zero. Okay? So we have to identify the condition as well as the property. So the condition or the restriction is that the y should not be non-zero. Okay, and its property is that its cube is not non-zero as well. So we can express this using implication. For all y, y is not equal to 0 implies that its cube is also not equal to 0. Suppose we have this another statement. There exists z greater than 0 and that z squared is not equal to 2. What does this mean in the domain of real numbers? So there exists a real number z with z is less than 0 and that z squared is not equal to 2. So what it means is, or expressing in natural language form, is there is a positive square root of 2. So this statement, we have to identify the restriction or the condition as well as the property and express it into this notation. So since this is existentially quantified, we will be using the and connective. Okay, so let's have some more examples. Suppose we have system specifications and that we have this statement for this specification. Every mail message larger than 1 megabyte will be compressed. And if a user is active, at least one network link will be available. So let us try to express each of this into its equivalent predicate form. So first is we have to determine or identify the individual predicates. So in this statement, can you deduce which ones are the individual predicates? So first one is that the mail message is larger than 1 megabyte. Okay, and that the mail message will be compressed. And for this statement, the user is active and that network link will be available. Okay, and now let us focus on this statement. Every mail message larger than 1 MB will be compressed. So as seen in the previous na slide, we have identified the individual na predicates. And now we will be introducing variables for each sentence. So let us identify the subjects. So we have the mail message as well as the 1 MB. So we have variables for each of these subjects. Mail message M is larger than 1 MB X. So we can express it in this predicate form, P of M and X, wherein mail message M is larger than 1 MB X. And wherein the domain of M is all mail messages and the domain of X is a set of positive real numbers. Because there is no such thing as a negative na megabyte. Okay, now the other predicate is mail message M will be compressed. Okay, so we can express this into a predicate Q of M such that mail message M will be compressed, wherein the domain of M is the set of all mail messages. So we can express this specification into a logical expression. So we can use the implication for this. And then what you have to do is check the sentence, and you can see that every mail message, meaning for all mail messages. And that means that we are going to use a universal quantification. And you know that in universal quantification, when we add restrictions, we make the restriction as the hypothesis to the implication or to the conditional na statement. And our restriction is that the mail message M is for it to be larger than 1 MB in order for us to compress the email or to compress the mail na message. Okay, so here we have for all M or for every message M, wherein that message M is larger than 1 MB. So as you can see, we have specified here the 1 MB. It implies that we are going to compress that mail message. Statement: if a user is active, at least one network will be available. We have already identified that one of the predicates is a user is active. And so we can express it in a predicate form, R of U, such that user U is active and that the domain of U is the set of all users. And then we have also another predicate, one network link will be available. So we have S of N such that N is a network link that will be available. And the domain of N is the set of all network links. Okay, so we can translate this specification to a logical expression. So we can express it using this. We have there exists U, or there is a user U that is active. If a certain user is active, then it implies that there will be one network. There is at least one network. So that's why we have another existential here. There is at least one network that will be available. Okay. And if you notice the structure of the sentence, it is expressed in an if-then structure, okay, wherein this serves as our hypothesis. And then this next statement will be served as our conclusion. Now, let us have another example. There exists X such that X is a real number and that the X squared is equal to 0. So which of the following are equivalent ways of expressing this statement? So first statement is that the square of each real number is 2. And this is not equivalent. Okay, so because here we are basically saying that every real number that we have, the square is equal to 2. Let's say consider 1, and if you take the square of 1, it's not equal to 2. And we can say that it is not equivalent. Then some real numbers have square root. And yes, this is equivalent because as you can see here, we are using an existential na quantifier, and that states there exists only some real number x that have a square of 2. Okay, and then if x is a real number, then x squared is equal to 2. And this is also not equivalent. Um, as you can see here, we are basically saying that if x is a real number, then its square is 2. And then same with the first statement. Suppose we have x which is equal to 1. If we take its square, it is not equal to 2, which can easily disprove this statement. So it is not equivalent to this statement. Now, if there is at least one real number whose square is 2, and this is also equivalent. Following sentences using predicates and quantifiers. First is that all lions are fierce, and then some lions do not drink coffee, and some fierce creatures do not drink coffee. So let us identify the individual predicates first and introduce variables to each predicate. So first is P of x such that x is a lion, and then Q of x such that x is fierce, and that R of x such that x drinks coffee. As you can see, it states that all lions, meaning for all of x such that x is a lion, so P of x, and that the lion are fierce. So meaning if x is a lion, then that x is also fierce. Okay, and then some lions do not drink coffee, and you can see a clue here. Some meaning there are only existing lions P of x such that they do not drink coffee. So we have to negated this statement. And third is some fierce creatures do not drink coffee. So from the statement itself, it says that some, so meaning there exists only some fierce creatures Q of x such that these creatures do not drink coffee. Okay, now let us proceed to the negation of quantified statements.